Welcome to our soil testing video series jointly presented by the Geotechnical Division of the HKIE and the Geotechnical Engineering Office of the CEDD. The production of this series is made possible by the generous support of our sponsors. In this video, we're going to explore an important aspect of soil testing, the compressibility characteristics of a soil, specifically its consolidation behavior. Have you ever wondered why buildings sometimes experience gradual settlement over time? Or, if you've been in the industry longer, have you ever needed to calculate the consolidation settlement in a reclamation project and determine the time it would take for consolidation to occur? These questions can only be answered by understanding the theory of consolidation and consolidation parameters of soil. What exactly is the meaning of consolidation of a soil? When a fully saturated soil is under additional applied loads, the pore water will first take up all the additional loads, which is known as excess pore water pressure. Consolidation refers to the gradual reduction in the volume of a fully saturated soil due to the dissipation of its excess pore water. This process continues until all the excess pore water pressure caused by an increase in the total stress on the soil is completely dissipated. As consolidation progresses, the effective stress in the soil increases gradually to accommodate the increase in total stress. At the end of consolidation, the increase in effective stress equals the increase in total stress. This indicates that the excess pore water pressure has completely dissipated, and this marks the end of the so-called primary consolidation. We must be careful not to mix up the consolidation with compaction. In consolidation, water is squeezed out from a fully saturated soil, which is dissipation of excess of pore water pressure. Hence, there is a decrease in moisture content of the soil. However, in compaction, it involves the reduction of the air voids in an unsaturated soil, and hence an increase in the soil density with very little change in moisture contents. So, how do we study the consolidation behavior of a soil? One of the key laboratory tests commonly used is the one-dimensional consolidation test, more commonly known as the odometer test. Here shows the setup of the odometer apparatus. It essentially consists of a loading frame, a vertical gauge to measure vertical deformation of the soil, a circular ring to accommodate the soil specimen, porous disc put on top and bottom of the soil which allows two-side drainage of excess pore water pressures, and a loading top cap. In this test, a soil specimen is subjected to a series of vertical pressures applied from the weight through the lever arm system of the loading frame. Each load increment is applied to the soil specimen for a sufficient duration until primary consolidation is completed. The vertical deformation and time taken are recorded. As the odometer permits the soil specimen to deform in the vertical direction only, with zero radial strain, the test is a one-dimensional consolidation test with only vertical straining and water flow. Hence, when you're using the results of odometer tests, please check the applicability of one-dimensional consolidation parameters to your project. That is to say, whether your site condition is in favor of one-dimensional vertical consolidation. This test is normally carried out for fine-grained soils and is not suitable for soils containing particles or inclusions with a size larger than about 1/5 of the height of the consolidation ring in the odometer. For the 70 mm diameter by 19 mm high ring commonly used in Hong Kong, tests on soil specimens containing particles or inclusions, for example shells, larger than about 4 mm may yield unreliable results. The test is also not suitable for soils containing unfavorable geological features such as joints and sand seams, which dominate the drainage characteristics of the soil sample. Detailed procedures for odometer tests are given in Test 14.1 of GeoSpec 3. The test begins by preparing a cylindrical soil specimen from a representative sample, such as piston sample, typically obtained from ground investigation. To prepare a specimen with a high degree of saturation, the specimen is soaked under water for at least 12 hours. In Hong Kong, marine or alluvial clays of low permeability are usually saturated or near saturated in their natural state. The soil specimen is then placed in an odometer cell equipped with a loading frame. A vertical gauge is put on top of the loading cap to measure vertical deformations. The uniform vertical stress is applied to the soil specimen by weights through the lever arm action of the loading ram. The test procedure involves applying incremental loads to the soil specimen. It could be loading, unloading, and reloading. The range of pressures applied are specified by the designer taking into account the stress range of the project. GeoSpec 3 allows a pressure range of 6 to 3,200 kPa, in which 12 to 800 kPa are commonly specified in Hong Kong projects. These incremental loadings allow us to observe the time-dependent compression of the soil under different stress levels. It also allows us to obtain the void ratio against log stress graph plot, which is an important output from the odometer test. We'll discuss this plot in more details later. When a soil specimen is under a particular vertical stress, vertical deformation continues with time. When do we stop this stage of test? Well, we stop it when the primary consolidation is ended. We call this EOP. How then do we know EOP is reached? In other words, how do we know how long is the primary consolidation period? During the test, we'll use two plots to show the real-time changes of the vertical deformation. One is a log time plot and another is a square root time plot. By using the methods as described in GeoSpec 3, each plot can give a primary consolidation period, and we take the longer one as reference to stop this stage of test. In the following, let's see how we can obtain some important compressibility-related parameters from the odometer test. Then we'll briefly describe how they can be used in practice. Here is a summary of the soil parameters that may be obtained from the odometer test. MV, CC, CR, and C secondary are related to the magnitude of consolidation. CV is related to the rate of consolidation. In addition, the E-log stress curve can be obtained and from which we know lots of information about the soil, including the pre-consolidation pressure. Knowing the end of primary vertical deformation under each vertical load, we may convert this deformation to EOP void ratio by this equation. Finally, we're able to draw the E-log stress graph as shown. The pre-consolidation pressure of soil may be estimated from the E-log stress graph by Casagrande's method. The compression index CC and recompression index CR are obtained from the slope of the curve as shown here. Lastly, the coefficient of volume compressibility MV under a specified stress range from sigma 1' to sigma 2' may be calculated from the E-log stress graph as illustrated. You must be aware that the MV value is dependent on the specified stress range. The CC, CR, and MV determine the magnitude of primary consolidation settlements. A larger value means larger compressibility of the soils under equal soil thickness and equal additional applied loads. The parameter for calculating the rate of consolidation settlement is the coefficient of consolidation CV. CV can be estimated from the odometer test by using the log time method and the square root time method under each vertical stress. In both equations, D is 1/2 the thickness of the soil specimen in the odometer ring. The value of CV determines the speed at which consolidation occurs. Soils with a high CV value consolidate more rapidly compared to soils with low CV value. To estimate the settlements due to primary consolidation, it is necessary to know the pre-consolidation pressure of the soils and the stress range of the project. Please refer to our video series on triaxial tests for a discussion of relevant stress range. As illustrated here, for an increase in stress within the compressible soil layer is smaller than the pre-consolidation pressure, for example from sigma 0 to sigma 1, CR is used in the calculation of settlement. Whenever the stress range goes beyond the pre-consolidation pressure, which is from sigma C to sigma F, CC should be used. In the equation shown, H is the thickness of the compressible soil layer on site. In addition to primary consolidation, there is secondary compression which occurs in the soils even when all the excess pore water pressure has completely dissipated. The soil parameter that characterizes the secondary compression is C secondary or C alpha. C secondary can be determined in the odometer test under a vertical stress as seen here. C alpha is related to C secondary through this equation. The settlement due to secondary compression may be calculated from this equation. T is the design life of the structure and TP is the time for completion of the primary consolidation. This wraps up our video on the methods for determining the one-dimensional consolidation properties of soils. We hope you have gained valuable insights on the theories, procedures, and the applications of these tests. Join us in the next video as we explore another exciting topic in soil testing. Thank you for watching.